Something is falling toward the sun right now, not drifting, falling. At 550 kilometers per second, a 2.4 kilometer comet is on a collision course with the solar corona, and it will arrive on April 4th, 2026. Scientists have never watched something this large enter the sun's outer atmosphere. Not once. Not with modern instruments. And here is the part they are not saying loudly at press conferences. If it fragments at the wrong moment, in the wrong magnetic region, the resulting chain reaction could send something toward Earth that makes every power grid on the planet a liability. Tonight we break down every worst case, ranked by how bad things could actually get. Stay with us until the end. The comet is still falling, the sun is still waiting, and the answer to what is the worst case will only be known on April 4th, 2026. Hit subscribe and keep us close, because this is one of those rare moments where science gets to watch something it has never watched before, and we intend to watch it with you. Part 1. The sungrazer that broke the pattern. Something is heading toward the sun right now, and it should not exist. Not in the sense that it defies the laws of physics. It exists. It is very real, and it is very large. But by every rule astronomers have built over decades of watching comets fall into our star, a comet this big, this bright, this far from the sun should simply not have been detectable. Not yet. Not from this distance. And the fact that we can see it at all is precisely what is making certain scientists put down their coffee and stare at their screens a little longer than usual. The comet is called C/2026A1, nicknamed MAPS, after the team that found it. On January 13th, 2026, astronomers Alain Maury, Georges Attard, Daniel Parrott, and Florian Signoret were scanning the southern sky from Chile's Atacama Desert using the AMAX 1 Schmidt telescope, a machine designed to catch faint, fast-moving objects against the dark. They caught one. It was sitting at 2.056 astronomical units from the sun, which translates to roughly 307 million kilometers. For most comets, that distance is completely unremarkable, but MAPS is not most comets. It belongs to a family where that distance is essentially unheard of. The Kreutz sungrazers are a population of comets infamous for one thing. They die near the sun, they plunge in close, they burn, and most of them simply vanish. NASA's SOHO spacecraft, which has been watching the solar neighbourhood for decades, has catalogued thousands of them. The overwhelming majority are tiny, fragments just a few meters across, essentially cosmic gravel. They are not discovered far away because there is almost nothing to discover. They only become visible when they are already close to the sun and already heating up. Weeks away from perihelion at most, sometimes days. So when MAPS showed up at over 2 astronomical units, almost twice the distance of the previous record holder, Comet Secchi, which was spotted at 1.11 astronomical units back in 1965, the immediate question was obvious. Why can we see it from so far away? The answer is uncomfortable in the best possible way. Something has to be reflecting enough sunlight at that distance to register on instruments sensitive enough to detect it, and when you do the math, the preliminary estimate for the nucleus diameter comes out to roughly 2.4 kilometers. 2.4 kilometers of rock and ice and frozen volatiles tumbling through space toward the most powerful object in our solar system. To understand why that number matters, you need to know what a typical Kreutz sungrazer looks like. The ones SOHO catches, the ones that flare briefly in coronagraph images and then disappear, tend to be a few meters wide. Some are perhaps tens of meters. Even the famous ones, the historically documented great comets that terrified medieval populations, are thought to have been fragments in the hundreds of meters to low kilometer range. 2.4 kilometers puts MAPS at the larger end of anything the Kreutz family has sent toward the sun in the modern era of scientific observation. We have not seen something like this before, not with the instruments we have now. The trajectory is already calculated. On April 4th, 2026, MAPS will reach perihelion, its closest point to the sun. It will skim the solar surface at approximately 163,000 kilometers above it. To put that in perspective, the average distance from Earth to the Moon is about 384,000 kilometers. This comet will pass within less than half that distance from the sun's visible surface. It will be travelling at approximately 550 kilometers per second, that is 340 miles per second. In 1 second, it will cover a distance greater than the distance from New York to Los Angeles. At that altitude, it will be inside the sun's corona, the outermost layer of the solar atmosphere, a region of superheated plasma that reaches temperatures in the millions of degrees Kelvin. Why the corona is hotter than the surface below it is a question solar physicists are still actively working to answer. What we do know is that it is a violently active, magnetically complex environment, and we are about to send a 2.4-kilometer object through it at nearly twice the speed that electrons orbit atomic nuclei. Here is the fundamental tension at the core of this entire story. You have a multi-kilometer comet, you have superheated plasma, you have solar cycle 25 operating near maximum activity, meaning the sun is already in an elevated, restless state. And you have a perihelion date circled on the calendars of solar physicists and comet observers around the world. The central question is not simply whether the comet survives, it is what the interaction itself might produce. In the most extreme scenario being discussed in scientific circles, the entry of this much material into the sun's magnetized plasma environment could destabilize existing magnetic structures and trigger a major solar eruption. April 4th, 2026 may become the first time in human history that modern science watches a large comet interact directly with the solar corona, in real time, with the full weight of 21st century instrumentation pointed directly at it. Or it may be completely unremarkable and we will all feel slightly foolish for worrying. The problem is, no one knows which of those two outcomes is more likely. And the reason they do not know brings us to something deeply strange about the comet's brightness, something that has observers checking their calculations twice, then a third time. Part 2. Why the brightness curve is making astronomers nervous. A comet's brightness is its biography. Every spike, every surge, every unexpected flare recorded in its light curve tells you something about what the nucleus is doing, whether it is cracking, outgassing, fragmenting, or holding together under the increasing pressure of solar radiation. When you track a sungrazer approaching the sun, and you plot how its brightness changes over time, you are reading a story written in reflected light, and the story Maps is telling right now is either reassuring or deeply unsettling, depending on how you interpret it. The scientific community is, at this moment, genuinely split on which reading is correct. The Comet Observation Database, known as COBS, has been logging reports from observers around the world. In January of 2026, MAPS was sitting at magnitude 17.8. By early March, it had climbed to roughly magnitude 11. If those numbers feel abstract, here is what they mean in practice. The magnitude scale runs backwards, lower numbers mean brighter objects, and each full step represents a brightness increase of 2.512 times. Going from magnitude 17.8 to magnitude 11 means the comet brightened by a factor of over 600 in approximately 2 months. 600 times brighter, and it is still accelerating toward the sun. The mathematical models, extended forward to perihelion, produce a number so extreme it almost defies description. Theoretical projections suggest the comet could reach magnitude -40, near its closest solar approach. -40. The full moon sits at magnitude -12.7. -40 would place MAPS at roughly 100 billion times the brightness of the full moon at its peak moment. You're not going to see that with your eyes. At perihelion, the comet will be separated from the centre of the sun by only 0.04 degrees in the sky. It will be completely drowned in solar glare. But that number is not meaningless. It is a measure of the raw energetic scale of what is happening, even if it exists only in the mathematics. The anomaly, the thing that actually makes observers nervous, is not the brightening itself. Brightening at this rate for a large sungrazer on approach is within the range of expectation. What is unusual is the shape of the curve. It has been smooth, remarkably, almost suspiciously smooth. No major outbursts, no sudden spikes, no evidence of the kind of thermal fracturing and jet activity that characterizes most large sungrazers as they heat up. When a comet nucleus is cracking and outgassing violently, you see it in the light curve as a sudden jump, a brightness surge that fades and stabilizes. MAPS has not done that. Not yet. Observers, including geophysicist Stephen Burns, who has been tracking the comet's evolution, have noted that the brightening is, in his framing, living up to expectations, steady, consistent, almost metronomic. That could mean one of two very different things. The first interpretation is optimistic. A smooth brightness increase could indicate a structurally strong, largely intact nucleus, a comet that is simply outgassing evenly as it warms, without catastrophic fracturing. That would suggest the nucleus is cohesive and dense, which in turn increases the possibility of survival through perihelion. The second interpretation is far less comforting. A smooth curve could mean that the real violence has not started yet, that we are watching the calm before fragmentation begins, a comet that is holding together for now, but has not yet experienced the full thermal shock of close solar approach. Think of it like watching a building during an earthquake. If the windows are rattling but the walls are holding, that could mean the structure is strong, or it could mean the main shockwave has not arrived yet. We will not know which until the shaking stops or the building falls. The honest answer is that comet science does not yet have the tools to definitively distinguish between these two interpretations from brightness data alone. What we can say is that the absence of outbursts is notable. Most observed sungrazers at this level of solar approach show activity in the light curve. MAPS is behaving unusually quietly, and in comet science, quiet does not always mean safe. Sometimes it means something is waiting. The real reckoning will come after perihelion. If MAPS survives the corona passage, if something emerges from behind the sun on the other side, the light curve will change dramatically and immediately tell us what survived. If nothing emerges, the light curve simply ends, the story closes. And if something enormous and unexpected happens in the solar environment during that passage, well, that story will be written not in reflected comet light, but in the behavior of the sun itself. Which brings us to a hypothesis that most mainstream solar physicists discuss carefully, and some discuss very carefully indeed, because the implications are significant enough that they deserve both serious attention and serious skepticism in equal measure. Part 3. The Plasma Cascade Hypothesis. The sun is not a fire. This is one of those scientific facts that sounds simple and then unfolds into something genuinely strange the longer you sit with it. Fire is a chemical reaction. The sun is a nuclear furnace wrapped in a magnetized plasma, and the distinction matters enormously for understanding what might happen when a 2.4 kilometer comet enters its outermost atmosphere at 550 kilometers per second. Because the rules that govern that interaction are not the rules of chemistry or even conventional thermodynamics. They are the rules of plasma physics, and plasma physics has a way of producing outcomes that are deeply counterintuitive. When MAPS enters the solar corona, several things will happen in rapid succession. The surface of the nucleus, already experiencing intense solar radiation, will undergo violent sublimation, the process by which frozen ices transform directly from solid to gas without passing through a liquid phase. Water ice, carbon monoxide, carbon dioxide, and various other volatiles will explode off the surface in enormous quantities, surrounding the nucleus in an expanding cloud of gas and dust. Under normal circumstances, this outgassing would simply add to the comet's coma and tail. But inside the corona, these neutrally charged gas molecules enter an environment dominated by charged particles and magnetic fields. And that is where things get complicated. The concept you need here was proposed by Nobel Prize-winning plasma physicist Hannes Alfvén, and it is called critical ionization velocity. The principle is this: when a cloud of neutral gas moves through a plasma at sufficient speed, it eventually reaches a threshold velocity at which the neutral particles begin to be ionized, stripped of their electrons, by collisions with the surrounding plasma. Once ionized, those particles are no longer neutral, they carry electrical charge, and charged particles in a magnetic field do not simply drift freely. They become coupled to the field lines. They follow the magnetic geometry of the environment they have entered. At 550 kilometers per second, MAPS is traveling well above the critical ionization velocity thresholds for most of the molecular species that comets contain. This means that as cometary gas pours off the nucleus and expands into the corona, a significant fraction of it will be ionized almost immediately, and those newly ionized particles will attach themselves to solar magnetic field lines, threading their way into the existing magnetic infrastructure of the corona. Now here is where the cascade scenario enters the picture. The solar corona is not an empty space with a few field lines floating through it. It is a densely structured magnetic environment, full of loops, arches, filaments, and flux ropes, enormous structures that store staggering amounts of energy. A large solar filament can contain plasma equivalent to trillions of tons, suspended in place by magnetic tension. These structures exist in a kind of dynamic equilibrium, a constant negotiation between magnetic pressure, plasma pressure, and gravity. They are stable until they are not. and when they destabilize, the results are well documented. They produce coronal mass ejections. The plasma cascade hypothesis proposes a specific chain of events. Cometary material enters the corona, it ionizes. The ionized material increases the mass loading along magnetic field lines connected to a coronal structure. The additional mass alters the equilibrium of the structure. If the perturbation is large enough, the magnetic structure becomes unstable and erupts, releasing its stored energy in the form of a CME. The key word in that sequence is if. If the perturbation is large enough. No one has ever tested this threshold with a comet of this size. The Kreutz sungrazers SOHO has watched for years are tiny. Their contribution to the coronal mass budget is negligible. MAPS is not tiny. MAPS is delivering potentially millions of times more mass than a typical sungrazer. Let us be precise about what this hypothesis is and is not. It is a scientifically grounded mechanism based on real plasma physics. It is also unproven. No direct observational confirmation of a comet-triggered CME exists that has survived rigorous statistical scrutiny. What exists are suggestive correlations, theoretical frameworks, and a very large unknown sitting at the centre of the problem. The mass threshold required to destabilise a coronal structure has never been experimentally determined because nature has never previously offered us an object of this scale to observe. April 4th, 2026 may be the experiment that finally gives us that data point. The question is whether we want it. Part 4. The CME trigger debate. Science is not a chorus. It is an argument conducted politely over evidence. Nowhere is that more visible right now than in the debate over whether a sun-grazing comet can trigger a coronal mass ejection. This is not a fringe discussion. It is a genuine, active disagreement among professional solar physicists, and it matters enormously for how we interpret what might happen on April 4th. On one side of this argument, you have researchers who look at the data and see coincidence. On the other, you have researchers who look at the same data and see a mechanism waiting to be confirmed. The skeptical case is strong and deserves to be stated clearly. The Sun during active periods generates dozens of coronal mass ejections every single day. In any given month near solar maximum, there may be hundreds of CMEs, each originating from different regions of the solar surface triggered by the Sun's own internal magnetic dynamics, completely independent of anything falling into it from outside. Thousands of Kreutz sungrazers plunge toward the Sun every year. If every sungrazer triggered a CME under the solar activity record would look very different from what we observe. Carl Battams of the US Naval Research Laboratory, one of the world's foremost experts on sun-grazing comets, has noted that the coincidences between observed sungrazers and subsequent CMEs are almost certainly statistical rather than causal. The Sun is simply active enough that something is always happening, and connecting two events that occur close together in time requires much more than temporal proximity. That is the skeptical position, and it is well reasoned. But here is the problem with applying it directly to MAPS, and this is the part of the argument where the counter-argument becomes genuinely difficult to dismiss. All of those thousands of sungrazers that have plunged into the corona without triggering anything unusual, they were tiny, meters wide. The mass they deposited into the coronal environment was negligible. When scientists argue that sungrazers do not trigger CMEs, what they are actually drawing on is a dataset composed almost entirely of objects that were too small to test the hypothesis meaningfully. In 1998, SOHO observed a pair of sungrazers disappear into the Sun shortly before a large CME was detected. Researchers have explored this correlation, and while it has not been confirmed as causal, it was significant enough to generate continued scientific interest. Studies presented at the European Geophysical Union have examined potential mechanisms for comet-induced CME activity. The 2014 work of Bryans and Pesnell modelled how cometary ions entering the corona could interact with magnetic structures. The modelling community has not dismissed the possibility. They have simply not had an object large enough to make the effect detectable above the noise floor of ordinary solar activity. Think of it this way. Imagine you want to know whether dropping a stone into a lake can create a wave large enough to disturb a ship anchored offshore. You test this by dropping pebbles into the lake, and you observe that the pebbles create no detectable waves at the ship. You conclude that stones do not create ship-disturbing waves. The logic is flawed because you have only ever tested pebbles. The relevant variable is mass, and you have never varied it enough to find the threshold. MAPS is not a pebble. The comparison to Shoemaker-Levy 9 is instructive here. When that comet's fragments impacted Jupiter over 6 days in July 1994, the atmospheric disturbances were visible from Earth with amateur telescopes. Jupiter is a gas giant with no magnetic corona. The effects were purely mechanical and thermal. The Sun is fundamentally different. It is a magnetized plasma star with stored magnetic energy orders of magnitude greater than anything a comet could release directly. But the Shoemaker-Levy 9 analogy illustrates a principle. A sufficiently large impactor interacting with a sufficiently large planetary system can produce effects that smaller objects cannot. The question for MAPS is whether sufficiently large means 2.4 kilometers, and the deeply uncomfortable truth is that we do not know. The mass threshold question sits at the absolute center of this debate, and April 4th will either provide us with a data point that begins to answer it, or it will produce a quiet, uneventful perihelion that pushes the threshold upward. Either outcome is scientifically valuable. Only one of them is potentially catastrophic. Part 5. The geometry that makes scientists uncomfortable. Timing in astrophysics is everything. A comet plunging into the Sun on the far side of the solar system, aimed completely away from Earth, is an astrophysical curiosity. That same comet, interacting with the solar corona while geometrically aligned to direct any resulting energy output toward Earth, is a different conversation entirely. And the geometry of April 4th, 2026, is one of the details that makes this event worth paying close attention to, not with panic, but with the kind of careful, wide-eyed attention you give to a situation where the margin between unremarkable and historic is not yet determined. On April 4th, the day of perihelion, MAPS will reach its closest point to the Sun at a position that places it almost directly behind the Sun from Earth's perspective. Astronomers call this a solar conjunction, and it has an immediate practical consequence. At the moment of maximum drama, the actual corona passage, we will not be able to see it directly. Every ground-based telescope on Earth will be staring into or near the solar disk. The comet will be hidden inside the glare of the very star it is diving into. But 2 days later, on April 6th, Earth reaches the comet's closest approach distance of 0.961 astronomical units. That is slightly closer than one full Earth-Sun distance. The Earth-Sun distance is already by definition 1 astronomical unit, so 0.961 places Earth essentially at the comet's orbital path, close to where MAPS was on its way in. And the significance of April 6th is not about the comet itself at that point. It is about what the Sun may be doing on April 6th in response to what happened on April 4th. Coronal mass ejections travel at varying speeds depending on how energetically they are launched. A slow CME moving at 300 to 500 kilometers per second takes roughly 2 to 4 days to travel from the Sun to Earth. A fast CME, launched at over 1,000 kilometers per second, can arrive in 15 to 20 hours. If a CME were triggered during the corona passage of April 4th and were directed even partially toward Earth, it could theoretically arrive during the window of April 5th through April 7th. The geometry does not guarantee this. Solar magnetic topology and the dynamics of individual CME launch geometry determine the actual propagation direction. Most CMEs, even Earth-directed ones, have a propagation cone wide enough that a slight misalignment means they miss entirely. What makes scientists uncomfortable is not any single element of this geometry. It is the combination. You have a large, unprecedented comet. You have a solar maximum that has already exceeded predictions. You have a perihelion geometry that places the event near the Sun-Earth line. And you have a 2 to 4 day travel time window that aligns with Earth's closest approach to the comet's orbital path. None of these factors individually constitutes a reason for alarm. Each one, taken alone, has precedent. But the specific combination, all of these variables converging simultaneously, is without direct historical parallel in the modern scientific record. The probability of a major Earth-directed CME triggered by this event remains extremely low. Every responsible scientist involved in monitoring this event will tell you that, and they are right to say it. The base rate of comet-triggered CMEs is, as we discussed, essentially unverified at this mass scale. The directional probability of a CME hitting Earth on any given day is low to begin with. The conditional probability, given all the caveats, is far lower than the kind of number that should produce public alarm. But you are here because you want to understand the worst case. And the worst case lives in that converging geometry, in that alignment of factors, in the fact that this particular natural experiment happens to be running on a timeline, and a trajectory that places Earth in a geometrically sensitive position at exactly the right moment to receive whatever the Sun decides to send. April 2026 could be routine. It could also be historic. The universe has not told us which yet. And that is precisely why we need to talk about what historic might actually mean. Part 6. The ancient comet that started it all. Every catastrophe has a family tree. MAPS did not appear from nowhere. It is, in all likelihood, a fragment of something much older and much larger, a traveller from the deep past of the solar system, a piece of an original body so immense that even its fragments, scattered across centuries of orbital time, have been producing historically significant comets for at least 2,000 years. To understand what MAPS might be, you have to understand the dynasty it may have come from. The Kreutz sungrazer family is named after astronomer Heinrich Kreutz, who in the late 19th century noticed something peculiar about several of the century's most spectacular comets. The Great Comet of 1843, the Great Comet of 1882, Comet C in 1965. They all shared nearly identical orbital elements, the mathematical fingerprints that describe a comet's path through space. Similar orbital inclinations, similar perihelion distances, similar times of perihelion passage adjusted for their respective dates. Kreutz concluded correctly that these were not independent objects. They were pieces of something that had broken apart. The theoretical ancestor, the progenitor comet of the Kreutz family, is estimated by some researchers to have exceeded 100 kilometers in diameter. 100 kilometers. For reference, the impactor that ended the Cretaceous period and removed the dinosaurs from the evolutionary record is estimated to have been approximately 10 to 15 kilometers wide. The Kreutz progenitor may have been 10 times larger. It was, by any measure, one of the largest coherent bodies ever to enter the inner solar system, and it did not survive intact. Ancient historical records may contain the shadow of this object. Aristotle reportedly described a spectacular comet around 371 BC. Ammianus Marcellinus, writing in the 4th century AD, recorded a comet in 363 AD that some researchers believe may represent an earlier fragment of the same ancestral chain. The orbital math, working backward through gravitational interactions and solar heating, suggests that C/2026 A1 may be a fragment with an orbital period of approximately 1,175 years. That puts its last perihelion passage in the vicinity of the 9th century AD, a period from which comet records are sparse but not non-existent. The fragmentation process that produces Kreutz comets is ongoing and cumulative. Each time a large fragment passes near the Sun, solar tidal forces, thermal stress, and outgassing torques crack it further. The gravel-sized fragments that SOHO watchers evaporate every week are likely the end products of this multi-generational breakup sequence. Dust from a giant that has been dying in slow motion for centuries. MAPS may represent a piece of the family that has been on its current orbit for over 1,000 years, travelling through the cold dark of the outer solar system while human civilizations rose and fell beneath it. Why does this history matter for the worst-case discussion? Because understanding the Kreutz family tells us something about what MAPS is made of and how it might behave. A fragment that has survived multiple previous close approaches to the Sun, if that is indeed what we are looking at, may be composed of structurally resistant material. The most volatile ices would have been driven off in earlier passages. What remains could be a denser, more refractory core. That increases the probability of survival through perihelion. And a surviving nucleus emerging from the corona passage would produce observable effects. A post-perihelion comet potentially bright enough to see in daylight, that would be scientifically extraordinary. But there is another possibility that the ancient lineage raises. Comets that have been in the inner solar system multiple times carry the scars of previous approaches, internal fractures, structural weaknesses built up over millennia of thermal cycling. A nucleus that looks intact from the outside may be riddled with internal fault lines, waiting for the precise thermal shock of a final close solar approach to let go all at once. Fragmentation at close solar distance does not produce a gentle dispersion of material. It produces a rapid, massive injection of cometary gas and dust directly into the corona. And that is precisely the input scenario the plasma cascade hypothesis requires. The ancient story of the Kreutz family is ultimately a story about scale meeting time. And time, in this case, has been building toward April 4th, 2026 for over 1,000 years. Part 7. The Lovejoy Precedent. Nobody expected Comet Lovejoy to survive. That is not a dramatic exaggeration for effect. That is the literal scientific consensus as it stood in December of 2011, when Comet Lovejoy, designated C/2011W3, was on final approach to a perihelion passage that would bring it to approximately 140,000 kilometers above the solar surface. Solar physicists and comet experts watched the data coming in from the SOHO and Stereo spacecraft and reached a broad agreement. This comet would not come back out. It was too close. It was moving too fast. The corona would consume it. On December 15th, 2011, Lovejoy reached perihelion. The models were right about one thing. The nucleus was almost certainly destroyed. But what happened next violated the expectations of virtually every researcher watching the event. The comet came out the other side. Not intact, the nucleus was gone, the coma was absent, but the tail persisted. A long, luminous, curving tail of material swept behind the comet's former head, still coherent, still visible, emerging from behind the solar disk into the clear field of view of the coronagraphs. Lovejoy had become a headless comet, a ghost of itself, still tracing its orbit even after the nucleus that had generated it was consumed. The footage captured by the Solar Dynamics Observatory during Lovejoy's corona passage is among the most remarkable solar imagery ever recorded. You can see the comet's path through the corona traced in extreme ultraviolet light, a bright streak cutting across the magnetic environment of the Sun. And in the immediate aftermath of the passage, the corona showed visible disturbances along the path of the comet's trajectory. Plasma oscillations, coronal loops responding to the passage. The magnetic environment was perturbed, not catastrophically, not in a way that triggered any unusual space weather event, but perturbed. The passage left a physical signature. Lovejoy's estimated nucleus size has been a subject of some uncertainty, with estimates ranging widely, but most analyses place it in the range of several hundred meters, significantly smaller than the 2.4-kilometer preliminary estimate for maps. This is where the Lovejoy precedent becomes both reassuring and alarming depending on which aspect of the comparison you emphasize. The reassuring version is this. A comet entered the corona at roughly similar altitude and speed, the nucleus was destroyed, and the Sun did not produce any anomalous space weather as a result. Normal service resumed. The alarming version is this. A comet significantly smaller than maps produced visible coronal disturbances during its passage. Whatever perturbation is caused by cometary material entering the corona apparently scales with the amount of material delivered. Maps will deliver more material than Lovejoy, potentially by a large factor. The Lovejoy event also taught us something important about comet structural resilience. The nucleus was destroyed, but the process took time. The comet survived its closest approach before the nucleus disintegrated, meaning it was intact during the most energetically intense phase of the corona interaction. A larger, denser nucleus, as maps may possess, could remain intact for even longer, delivering its cometary material more coherently and more deeply into the coronal magnetic environment, before finally yielding to the forces working against it. There is also a survival possibility that the Lovejoy precedent opens. If a comet the size of Lovejoy could produce a coherent post-perihelion tail, even after nucleus destruction, a comet with a nucleus 2 to several times larger might retain at least a fragment of its nucleus through perihelion. A surviving MAPS would be a fundamentally different kind of spectacle than any comet seen in the modern era. It could become bright enough to observe in broad daylight. It could produce a tail spanning degrees of sky. It could be, in the literal sense of the term, the comet of the century, the brightest object in Earth's sky, apart from the Sun itself. Those two outcomes are not separate stories, they are the same story from different angles. A surviving MAPS is spectacular. A disintegrating MAPS inside the corona is potentially dangerous. Both possibilities branch from the same approach, and the branch point is April 4th, 2026. Part 8. What if the comet actually hit the Sun? Let us address the scenario that your imagination has probably already constructed. The comet misses or does not miss. What if the orbital calculations are wrong, and instead of skimming 163,000 kilometers above the solar surface, MAPS hits the Sun directly? Before we follow that thread, we need to establish what the current numbers actually say. because the distinction between a close flyby and a direct impact is not just dramatic, it is scientifically fundamental. Current orbital calculations place the perihelion distance at 0.005744 astronomical units, with an uncertainty of plus or minus approximately 5,000 kilometers. The solar radius is about 696,000 kilometers. A perihelion at the calculated distance keeps maps well above the photosphere, the visible surface, by around 163,000 kilometers. Even accounting for the uncertainty range, the probability of a direct photospheric impact is statistically ruled out by the current orbital solution. Each new observation refines the orbit further, and so far the calculations have been consistent. But let us do the thought experiment anyway, because the thought experiment reveals something important about scale. What would happen if a 2.4 kilometer comet struck the Sun directly at 550 kilometers per second? The Sun is not a fragile object. It is a sphere of plasma and nuclear reactions with a mass approximately 330,000 times that of Earth. Comet MAPS, at its estimated size, has a mass somewhere in the range of perhaps 10 to 20 billion tons, a number that sounds enormous until you compare it to the Sun's mass of roughly 2 times 10 to the power of 27 metric tons. The comet represents an addition to the solar mass of approximately 1 part in 10 to the 17th. It is like throwing a grain of sand into the Pacific Ocean and asking if the ocean level changes. The direct energy contribution of the impact would be real but cosmically insignificant. Kinetic energy delivered at 550 kilometers per second is substantial, roughly equivalent to tens of thousands of nuclear weapons worth of energy. But the Sun radiates that same amount of energy every fraction of a millisecond in its normal operation. The Sun would not notice. What it might produce, however, is a localized atmospheric disturbance visible to solar telescopes. The Shoemaker-Levy 9 impacts on Jupiter, which we mentioned earlier, produced scars in the Jovian atmosphere that were individually visible from Earth and persisted for weeks. Jupiter is a gas giant with a fraction of the Sun's energy output. The Sun would almost certainly produce a visible impact plume, perhaps a localized brightening, possibly a seismic wave rippling through the solar atmosphere, helioseismic disturbances that solar physicists have modelled theoretically. Whether that localized disturbance could couple into a CME depends on the same magnetic topology questions we have been discussing. Here is the important clarification for the direct impact scenario. The most dangerous version of this event is not a direct hit. The most dangerous version is almost certainly the near miss, specifically a fragmentation event inside the corona at the depth of close perihelion passage, where the comet disintegrates over a sustained distance within the most magnetically active region of the solar atmosphere, injecting material continuously across a long coronal trajectory rather than depositing it in one point. A direct impact is a bullet. A fragmenting sungrazer in the corona is a shotgun blast spread across hundreds of thousands of kilometers of magnetized plasma. The latter is almost certainly more disruptive to the magnetic architecture of the corona than the former. So the direct hit, while dramatic in imagination, may actually be the less concerning scenario. The one we should be thinking carefully about is the quiet, gradual dissolution inside the corona, and we have already established that this is exactly what a 2.4 kilometer Kreutz sungrazer is likely to do. Part 9. The Electric Universe Interpretation. Every major scientific event attracts a chorus of alternative interpretations, and MAPS is no exception. Across corners of the internet and in certain independent research communities, the approach of this comet is being discussed not through the lens of plasma physics and nuclear solar models, but through the framework known as the electric universe hypothesis. It is worth understanding what this framework claims, why it attracts followers, and why mainstream astrophysics maintains a deep skepticism about its core assertions. Because understanding the boundary between legitimate plasma science and unsupported speculation is important when evaluating claims about an event this significant. The electric universe hypothesis, developed largely through the work of Wallace Thornhill and David Talbot, proposes that electromagnetic forces play a far more dominant role in shaping cosmic structures than conventional physics acknowledges. In the standard model of solar physics, the Sun is powered by nuclear fusion in its core, and its external behavior, flares, CMEs, corona heating, is driven by magnetic field dynamics generated by plasma flows. In the electric universe framework, the Sun is instead conceptualized as a large anode in an electrical circuit, sustained by galactic-scale electrical currents rather than internal fusion. Comets, in this model, are treated as electrically charged bodies moving through an electric field, and their behavior near the Sun is interpreted as electrical rather than thermodynamic in nature. The characteristic features of comets, their comas, their tails, their sudden outbursts, are attributed to electrical discharge events rather than sublimation of ices. There is a reason this framework attracts genuine attention, and it deserves to be acknowledged. The language of the electric universe overlaps significantly with actual plasma physics terminology. Words like ionization, plasma currents, magnetic reconnection, and electrical coupling are all real phenomena in solar science. The electric universe community is correct that plasma behavior and electromagnetic forces are central to solar dynamics. Where the framework diverges sharply from mainstream science is in the specific mechanisms it proposes and, critically, in its resistance to quantitative testing. Mainstream solar physics is built on predictions that have been tested against observations with extraordinary precision: helioseismology, CME propagation models, solar wind dynamics, all have been verified to degrees of accuracy that alternative frameworks have not matched. The claim that MAPS, as an electrically charged body, might interact with the Sun's alleged electrical circuit in ways that produce anomalous energy releases is, in the electric universe framework, a central prediction. Proponents of this view are paying close attention to April 4th and will likely interpret any unusual solar activity during or after the perihelion passage as confirmation of their model. This is worth noting, not because the electric universe is scientifically validated, but because it illustrates a genuine human cognitive tendency. We find the interpretive framework that fits our prior beliefs and filter events through it. What is genuinely interesting about this situation from a scientific standpoint is that the conventional plasma physics explanation and the electric universe interpretation sometimes predict similar observable outcomes through completely different mechanisms. If something unusual does happen to the solar corona during MAPS's passage, both communities will claim it as evidence. The difference is that mainstream solar physicists have a mathematically coherent, observationally supported framework that makes testable predictions. The electric universe does not yet offer the same level of quantitative testability. For our purposes, the takeaway is this: the plasma physics of what MAPS will do inside the corona is genuinely extraordinary, based entirely on well-established science. You do not need alternative cosmology to find this event remarkable. The standard model gives you more than enough to work with, and the boundary between scientific caution and speculative excitement is one worth keeping clearly in view as April 4th approaches. Part 10. The Carrington Event Problem. In September of 1859, the Sun sent Earth a message, and Earth was not equipped to receive it gracefully. The Carrington event began on September 1st of that year, when British astronomer Richard Carrington sat at his telescope and observed something that had never been formally documented before: an intensely bright eruption on the solar surface, a white light flare so powerful it was visible to the naked eye through his instrument in broad daylight. Carrington was a meticulous observer. He noted the time, sketched the position, and documented what he saw with the careful precision of a man who understood he was watching something unusual. What he could not have known was that 17 hours later, the fastest coronal mass ejection ever recorded in human history would arrive at Earth and introduce his name to every space weather textbook written in the following century and a half. What followed that arrival was the most powerful geomagnetic storm in the historical record. Auroras appeared as far south as Cuba and Hawaii, latitudes where the northern lights have no business appearing under normal circumstances. The skies over the Rocky Mountains glowed so brightly that gold miners woke from their sleep convinced the sun had risen early and began preparing for the day. Telegraph operators across North America and Europe reported something that, without context, would sound like a ghost story. Their equipment was sparking, catching fire, delivering electrical shocks, and this was happening even after the systems had been deliberately disconnected from their power supplies. The induced electrical currents flowing through the telegraph lines from the geomagnetic storm were powerful enough to operate the equipment independently, transmitting messages through copper wire energized entirely by the sun's fury, rather than any battery on Earth. That was 1859. Pause on that for a moment, because the context of that year matters enormously for understanding why this event, as catastrophic as it sounds, was ultimately survivable in a way that a repeat performance would not be. The global electrical infrastructure of 1859 consisted largely of telegraph lines, copper wire strung between wooden poles across open countryside. The damage was dramatic, it was alarming, it was, by the standards of that era, genuinely shocking. But the planet in 1859 was not dependent on electricity for its food supply. It was not dependent on electricity for its water treatment, its financial systems, its medical equipment, its communications networks, its fuel distribution, or the 1,000 other invisible services that modern civilization has quietly built its entire operating system upon. The telegraph was remarkable technology for its time. Losing it for a few days was disruptive, it was not existential. We are now describing a civilization that would experience a Carrington-level event in a fundamentally different way, not just a more expensive way, a structurally different way, where the failures cascade across interconnected systems in a sequence that planners have modelled and that keeps certain categories of infrastructure engineers awake at night in a way that is not entirely metaphorical. Lloyd's of London is not an organisation given to alarmism. They are an insurance market. Their entire business model depends on accurate risk assessment rather than theatrical catastrophising. When Lloyd's published an estimate suggesting that a Carrington-equivalent geomagnetic storm today could cause between $0.6 and $2.6 trillion in economic damage in the United States alone, that number did not come from a disaster film screenplay. It came from actuaries doing mathematics on asset inventories, replacement cost schedules, and cascading failure models. $2.6 trillion in the United States alone, and that figure does not fully capture the downstream human cost of the infrastructure losses it represents. The particular vulnerability that concerns engineers and policy analysts most is not your laptop. It is not your phone. Consumer electronics, while they would be damaged or destroyed in a severe event, are recoverable on timescales of months. The global manufacturing capacity exists to replace them. The critical vulnerability, the one that sits at the centre of every serious Carrington scenario planning document, is large high-voltage transformers. These are the enormous devices that perform the essential translation between transmission-level voltages and the usable voltages that reach homes, hospitals and factories. They are not the transformers on neighbourhood utility poles. They are the massive building-sized units at major substation facilities. They weigh hundreds of tons each. They are not manufactured off a standard production line. They are custom-built to specification, with lead times under normal manufacturing conditions of 12 to 18 months per unit. Some estimates place the number closer to 2 years for the largest classes. A Carrington-level geomagnetic storm works on these devices through a specific physical mechanism. The storm drives enormous induced electrical currents through the ground, through any long conductive material actually, including power lines, pipelines and railway tracks. These ground-induced currents enter the power grid through grounding connections and flow into the cores of large transformers. The problem is that these currents are quasi-direct current, not the alternating current the transformers are designed to handle. When quasi-DC current saturates a transformer core, the transformer overheats, severely, rapidly. In a major geomagnetic storm event, models suggest that hundreds of large high-voltage transformers across North America, Europe and Asia could fail simultaneously or in rapid succession. Without those transformers, the sections of the power grid they serve cannot be restored until the transformers are replaced. And replacement, as we established, takes 12 to 18 months minimum under normal production conditions, conditions that would themselves be compromised if the manufacturing facilities for transformer components are also experiencing power grid failures. The cascading consequences extend far beyond dark houses and dead phone batteries. Water treatment plants stop functioning, and municipal water pressure fails within days. Refrigeration fails across the food supply chain simultaneously. Fuel distribution systems, which depend on electrically powered pumps throughout the pipeline and retail network, cease operating. Hospital backup generators, designed for days, not months of autonomous operation, eventually run out of fuel that cannot be resupplied through a non-functional distribution network. The picture that serious infrastructure analysts describe is not apocalyptic in a cinematic sense. It is grimly, quietly catastrophic in a logistical sense. A civilization whose complexity has outpaced its resilience, confronting a natural event that its Victorian-era predecessor survived with relatively modest consequences. In July of 2012, humanity received a warning that was quiet only because most people were not paying attention. A solar eruption approximately equivalent in total energy to a Carrington-class event occurred on the Sun's surface. It launched a coronal mass ejection of extraordinary speed and energy into interplanetary space. The CME travelled outward from the Sun along a trajectory that passed through Earth's orbital path, and it missed. It missed Earth by 9 days of orbital rotation, meaning if the eruption had occurred 9 days earlier in the calendar, when Earth was at the position in its orbit that the CME actually passed through, it would have been a direct hit. 9 days. On an orbital journey of 365 days, the margin between a near miss and a civilization-altering direct hit was 9 days. Researchers who subsequently analysed this 2012 near miss estimated the probability of a Carrington-class event hitting Earth in any given decade at between 10 and 12%. Take a moment to sit with that number, because it tends to get lost in the abstraction of percentage points. 10 to 12% per decade means that in any given 50-year period, the cumulative probability of at least one Carrington-class event hitting Earth approaches 50%. We are not talking about a once-per-millennium catastrophe safely beyond the planning horizon of any current institution. We are talking about a recurring natural threat on timescales, directly relevant to the service life of infrastructure being built today, power plants, grid systems, and transmission networks designed to operate for 30, 40, 50 years. The specific scenario that April 4th, 2026 raises in the context of everything we know about the Carrington event is this. The Sun produced Carrington entirely on its own, from its own internal magnetic dynamics, without any external input or perturbation. It required no comet. It required no unusual alignment of solar system geometry. It required only the Sun behaving as the Sun occasionally behaves, storing enormous magnetic energy in coronal structures and releasing it suddenly. That happens. It will happen again. The question MAPS introduces is different and genuinely new. Can an external perturbation of the solar corona assist the Sun in reaching that threshold earlier or more energetically than it would have on its own? That question has never been testable before, because no previous sungrazer observed in the modern era has been large enough to meaningfully perturb coronal magnetic structures. The probability of a MAPS-triggered Carrington-class event remains low. Every honest assessment of this scenario returns to that baseline, but low and impossible are separated by a distance that matters. Carrington happened once at full intensity without any external trigger. The geometry of April 4th places Earth in the most unfavourable alignment it could occupy if a CME were generated by the corona interaction. And the Sun is currently operating at a level of activity that has exceeded its own forecast for this cycle. The question April 4th, 2026 raises is not whether the Sun will produce another Carrington event. It will eventually, with or without any comet's assistance. The question is whether we are about to watch the external trigger for that kind of event arrive in real time, observed by instruments sensitive enough to confirm what happened, on a timeline compressed by orbital geometry into something that would give us very little warning and even less time to prepare. That question does not have an answer yet. April 4th will either provide one, or it will give us a quiet perihelion and push the concern back into the background where it usually lives. Either way, the Sun has always been the most powerful object in our immediate cosmic neighbourhood. MAPS is simply the first object in modern history large enough to remind us that we have never fully tested what that means. Part 11. The Solar Cycle. 25 Surprise. The Sun was supposed to be quiet. That was the official position as recently as a few years ago, and it was not an unreasonable one. Solar activity follows a roughly 11-year cycle, oscillating between periods of relative calm, solar minimum, and periods of elevated activity, solar maximum, driven by the build-up and release of magnetic energy generated by the Sun's differential rotation. The cycle has been documented continuously since the mid-18th century, giving scientists nearly 300 years of observational data from which to build predictive models. When Solar Cycle 25 began around 2019, NASA and NOAA looked at that historical record, looked at the behaviour of the preceding cycle, and arrived at a cautious, carefully hedged forecast. Based on the relatively subdued performance of Solar Cycle 24, which had been one of the weakest cycles in a century, the predictions called for a below-average or at most average cycle. scientists expected a modest solar maximum, a manageable peak in sunspot counts, and a generally calm period for space weather running roughly from 2024 through 2026. The model suggested we had breathing room. The Sun, the forecast implied, was entering a quiet phase. The Sun did not read the forecasts. Solar cycle 25 has exceeded its predicted intensity by a margin that has required forecasters to revise their models multiple times since the cycle began. Sunspot counts have run well above official projections for multiple consecutive years. The cycle has produced X-class flares, the most energetic category in the standard classification system, at rates that consistently outpaced early cycle expectations. Coronal mass ejections have been occurring with a frequency and intensity that has kept space weather monitoring teams at agencies around the world in a state of sustained operational alertness, rather than the routine watchfulness the original forecasts implied. The gap between what the models predicted and what the Sun delivered has been wide enough and persistent enough to prompt genuine scientific discussion about the limitations of current solar cycle forecasting methodology. This matters for the MAPS story in a way that is not merely contextual. The state of the Sun on any given day is not just background information. It is the operating environment into which every event, every flare, every CME, every infalling object is introduced. A quiet Sun sitting near solar minimum with few active regions and relatively simple magnetic topology is a fundamentally different system than a Sun near maximum that is already generating energetic events from its own internal dynamics on a daily basis. The difference is not just quantitative, it is qualitative. The corona near solar maximum is structurally more complex, carrying more stored magnetic energy, distributed across more numerous and more densely packed magnetic structures. The probability of any given perturbation finding a primed, energy-loaded structure to interact with is simply higher when the Sun is more active. By the time April 4th, 2026 arrives, solar cycle 25 will be at or very near its maximum phase. The solar disk will in all likelihood carry multiple active regions simultaneously, clusters of complex high-energy magnetic field configurations that represent the highest probability sources of major flares and CMEs on the entire solar surface. The corona above those regions will be threaded with flux ropes, magnetic loops, and filament channels, each one a stored energy system in dynamic equilibrium, each one susceptible to the kind of perturbation that tips equilibrium into eruption. This is the specific environment into which MAPS will be delivering its cometary material at 550 km per second. Not the quiet, relatively simple corona of a solar minimum, the complex, energized, already restless corona of a solar maximum that has been running hotter than anyone predicted. The significance of this timing is best understood through a framework that solar physicists use when analyzing how eruptions sometimes cascade beyond what the initial trigger would seem to warrant. The question is not simply whether the comet's interaction with the corona produces a perturbation. The question is whether the perturbation needs to be large to have significant consequences, or whether it only needs to be the right kind of perturbation delivered to a system that is already sitting close to a release threshold. These are very different requirements. The first demands that MAPS deliver enough energy or mass to independently destabilize a coronal structure. The second only demands that MAPS deliver enough of a nudge to push a structure that was already approaching instability over the edge. Think of it in terms of a physical analogy that most people have encountered without necessarily connecting it to solar physics. A steep slope covered in fresh, heavy snow does not avalanche at a random moment for no reason. It avalanches when it reaches a stress threshold, and that threshold can be crossed by an enormous external force, or by a single skier crossing at the wrong moment, or sometimes by nothing more dramatic than a slight temperature change, altering the cohesion of a single internal layer. The size of the trigger is not the determining variable. The proximity of the system to its own threshold is the determining variable. A spark does not need to be large if the material around it is already primed to burn. It needs only to arrive. Solar physicists call this dynamic triggering, and it is a recognized and documented feature of how solar eruptions sometimes behave. A small magnetic instability in one region couples to adjacent structures. A minor flux rope destabilization initiates a reconnection event that releases energy from a neighboring, larger structure that had been accumulating stress for days. The initial event, examined in isolation, would not seem capable of producing the observed outcome, but it did not operate in isolation. It operated in a system already loaded with energy and already close to releasing it. The trigger was small, the response was not. Solar Cycle 25's unexpected strength has already demonstrated this principle in practice. Several significant geomagnetic storms have occurred during this cycle, at levels not seen in decades, some of them surprising forecasters with their intensity relative to the active regions that appeared to initiate them. The May 2024 geomagnetic storm, one of the strongest in approximately 20 years, produced auroras visible at latitudes that had not seen them in a generation. That event was driven entirely by the sun's own dynamics, without any external input. It was a reminder, arriving well ahead of April 4th, that the current cycle is capable of producing major space weather events, and has already done so multiple times. Infrastructure operators and space weather forecasting agencies have been tracking this elevated activity with a level of attention that reflects the sustained nature of the cycle's performance. The monitoring networks watching the Sun, SOHO, the Solar Dynamics Observatory, NOAA's Space Weather Prediction Centre, the European Space Agency's Space Weather Service network, will not be approaching April 4th from a standing start. They will arrive at that date already in an operational posture shaped by a cycle that has been delivering surprises since it began. The monitoring systems will be alert, the forecasting models will be running. The question is whether the event they are monitoring will fall within the range those models were built to handle, or whether it will represent something genuinely outside their training data. The combination of an unexpectedly active solar cycle and the arrival of an unprecedented sungrazer creates a compounding situation that is worth describing precisely. In April 2026, the baseline space weather risk, the risk from the Sun's own activity, entirely independent of any comet, is already elevated relative to what forecasters expected when this cycle began. The Sun is already more active, already more complex, already generating more and larger events than the model suggested it would be at this stage. Into that already elevated baseline, maps will arrive, not into the calm, manageable solar environment the 2019 forecast described, into a sun that has been consistently exceeding expectations for 6 years, that is sitting at or near the peak of a stronger than predicted maximum, and that is carrying in its corona the accumulated magnetic energy of a cycle that has not yet finished surprising people. The honest framing of what this means is not that Solar Cycle 25's unexpected strength makes a MAPS-triggered event likely. It does not. Probability assessments throughout this discussion have been consistent, and they do not change here. What the cycle's strength does is alter the conditional landscape in which the April 4th interaction takes place. It raises the floor. A comet entering a more magnetically energized corona is not the same as a comet entering a quieter one, even if the comet itself is identical. The threshold for dynamic triggering is lower when the system is already loaded. The number of primed structures available to interact with is higher. The background noise of solar activity against which any anomalous signal must be detected is louder, making the signal harder to isolate in real time but no less real if it exists. The Sun was supposed to be quiet in 2026. It is not quiet, and MAPS is arriving anyway. Part 12. The Rise of Interstellar Visitors. Something happened in October of 2017 that permanently changed how astronomers think about what passes through our solar system. The change was not gradual. It did not arrive through the slow accumulation of data points that characterizes most shifts in scientific understanding. It arrived in a single observation made by Robert Werrick using the Pan-STARRS telescope at the Haleakala Observatory in Hawaii, when he detected an object moving through the inner solar system on a trajectory that could not be explained by any origin within our solar system. The object was designated Oumuamua, a Hawaiian word meaning roughly a messenger from afar arriving first. The name turned out to be more appropriate than anyone initially appreciated, because what Oumuamua delivered was not just an observation, it was a conceptual disruption. Before October 2017, interstellar objects passing through our solar system were a theoretical prediction. After October 2017, they were an observational reality. That distinction matters more than it might initially appear. Oumuamua's behaviour was strange from the beginning, and it became stranger the more carefully astronomers studied it. The object was tumbling, rotating in an irregular end-over-end motion that suggested either an unusual shape or an asymmetric mass distribution. The shape itself was deeply puzzling, Light curve analysis, which tracks how an object's brightness changes as it rotates and reveals information about its geometry, suggested something extremely elongated, described variously as resembling a cigar or, in later modelling, a thin flat disk, like a cosmic pancake skimming through interplanetary space. Neither shape has a straightforward explanation in the context of objects that form naturally in planetary systems, though various formation mechanisms have been proposed for both. The most scientifically significant anomaly emerged as Oumuamua departed the solar system. Its trajectory did not follow the path that gravitational physics alone would predict. It was accelerating beyond what gravity accounted for, moving faster than it should have been, on a trajectory slightly different from the purely gravitational one. This non-gravitational acceleration in a comet would typically be attributed to outgassing, the rocket-like push that results when volatiles sublimate off the nucleus and propel the object in the opposite direction. But Oumuamua showed no visible outgassing, no coma, no detectable gas or dust emission at the sensitivity levels of the instruments watching it. The explanation for its extra acceleration remains, as of 2026, genuinely unresolved. Hypotheses range from radiation pressure on an unusually thin, flat object, to outgassing of hydrogen too diffuse to detect directly, to more exotic proposals that the scientific community has received with varying degrees of enthusiasm. What has not been proposed successfully is a conventional explanation that fully satisfies all the observational constraints simultaneously. What Oumuamua confirmed, beyond any of the interpretive debates about its nature, is a single foundational fact. Objects from other stellar systems enter our solar neighbourhood. This is not a hypothetical. It is not a theoretical prediction awaiting confirmation. It has happened. We watched it happen. And because Oumuamua was only detected after it had already passed its closest approach to the Sun and was on its way out, we observed it under the worst possible circumstances, receding, fading, with the most scientifically interesting phase of its trajectory already completed before we knew it existed. 2 years after Oumuamua, the picture clarified considerably. In August of 2019, amateur astronomer Gennady Borisov detected an object from his observatory in Crimea that would become the first confirmed interstellar comet. Where Oumuamua had been enigmatic and behaviourally anomalous, Comet Borisov was almost reassuringly familiar. It showed outgassing, it developed a coma, it produced a tail. Spectroscopic analysis of its composition revealed molecular signatures broadly consistent with solar system comets, water ice, carbon monoxide, dust grains in ratios that overlapped with the range observed in comets that formed around our own Sun. Borisov arrived from interstellar space, looking and behaving like something that could have been born in our own planetary system, and simply wandered away from it. The implication was significant and immediate. Comets are not unique to our solar system. They form around other stars, and they are exchanged between stellar systems through the gravitational dynamics of galactic motion, with enough regularity that 2 interstellar visitors were detected within 2 years of each other, using survey technology that was not specifically designed or optimized to find them. The detection rate of 2 interstellar objects in the span of roughly 24 months, using existing survey infrastructure, allowed researchers to begin estimating how many such objects actually pass through the inner solar system. The numbers are substantial. Models suggest that at any given time, there may be several interstellar objects within the orbit of Neptune, most of them undetected because they are too small and too faint for current instruments to find, unless they pass very close to Earth, or, in the case of comets, develop enough outgassing activity to brighten significantly. The inventory of objects moving through our solar system at any given moment is almost certainly larger than pre-2017 models suggested, and a meaningful fraction of that inventory originated around other stars entirely. This matters for the broader context of maps, and not merely in a philosophical sense. The specific relevance is what is coming next in solar system survey capability, and what that means for our ability to anticipate events like the April 4th perihelion with adequate warning time and observational preparation. The Vera Rubin Observatory, constructed on Cerro Pachon in the Chilean Andes, represents the next significant step in humanity's ability to monitor the solar system comprehensively. Its primary instrument, the Legacy Survey of Space and Time, LSST, is a decade-long program designed to image the entire accessible sky every few nights to a depth and resolution that substantially exceeds any previous wide-field survey. The combination of aperture, field of view, cadence, and data processing capability gives Vera Rubin a detection sensitivity for faint, fast-moving objects that no previous facility has approached. When LSST reaches full operational capacity, estimates suggest it could detect between 10 and 100 times more interstellar objects per year than current surveys. It will also detect solar system comets, asteroids, and other small bodies at earlier stages of their approach trajectories, catching objects at greater distances, with more time remaining before any significant event, and with sufficient data density to determine orbits with high precision from the outset, rather than accumulating orbital refinements over weeks of follow-up observation. The Vera Rubin Observatory would, in all likelihood, have detected MAPS significantly earlier than January 2026. The discovery at 2.056 astronomical units was already unprecedented for a Kreutz sungrazer. Vera Rubin's capabilities suggest that future large sungrazers on similar trajectories could be identified at 3, 4, or even 5 astronomical units, potentially months earlier than the current discovery, with correspondingly more time for detailed characterization, refined orbit determination, and scientific preparation. The era of being genuinely surprised by objects of this significance is, if not ending, at least contracting. The tools being built and deployed right now are specifically designed to shrink the category of unknown unknowns in the solar system inventory, to ensure that the next large sungrazer, the next interstellar visitor, the next object whose trajectory intersects the inner solar system in a way that demands serious scientific attention, is found early enough for the full weight of observational resources to be brought to bear before the critical event rather than during or after it. What Oumuamua and Borisov together suggest about the broader picture is worth sitting with for a moment, because it reframes not just MAPS, but the entire class of events MAPS represents. Before 2017, the solar system felt, in a certain sense, like a closed system. Objects moved within it, perturbed each other gravitationally, occasionally collided, gradually evolved. The stars were background. The boundary between our solar system and everything else was largely conceptual, but also, in practical observational terms, uncrossed. Oumuamua crossed it. Borisov crossed it more recognizably, and the statistical implication of 2 detections in 2 years, with instruments not optimized for the search, is that the crossing happens routinely, that our solar system is not an island but a waypoint, constantly receiving visitors whose origins lie around other suns, in other planetary formation histories, potentially in environments nothing like our own. The universe is not stationary. Material moves through it on timescales that are long by human standards, but routine by galactic ones. Some of that material is small, some of it is large. Some of it, by the unremarkable operation of orbital mechanics and gravitational dynamics, ends up on trajectories that carry it toward the Sun at the same time Earth occupies a geometrically sensitive position relative to whatever that approach might produce. MAPS may be the first event in the modern era of solar observation to combine an unprecedented object size, a solar maximum background, and an unfavourable Earth geometry into a single convergent scenario. The probability remains low that any of the worst-case outcomes will materialise. But the more important point is structural rather than probabilistic. This will not be the last time these variables converge. The inventory of objects capable of producing this kind of event is larger than we thought before 2017. Our ability to find them early is improving, and the gap between finding them early and being able to do anything meaningful in response remains a question that neither the Vera Rubin Observatory nor any instrument currently in development has yet answered. We're getting better at watching. Whether we are getting better at being ready is a different question entirely, and April 4th, 2026 may be one of the first real tests of the distinction. Part 13, AI is now predicting solar storms. For most of the history of solar observation, forecasting space weather was essentially an expert judgment exercise. The process looked, from the outside, something like this. A trained analyst would arrive at a workstation covered in solar imagery, magnetograms showing the magnetic polarity distribution across the solar surface, extreme ultraviolet images revealing the thermal structure of active regions, coronagraph data showing the state of the outer solar atmosphere. They would evaluate the magnetic complexity classifications of active regions using a standardized system developed over decades of observation. They would consider recent flare history, look for the kinds of magnetic configurations historically associated with eruptions, apply accumulated experience about how those configurations tend to evolve, and produce a probabilistic forecast. 30% chance of an M-class flare in the next 24 hours, 15% chance of an X-class event, elevated CME probability from active region number such and such. The forecast would be issued, distributed to grid operators and satellite managers and aviation authorities, and then revised again the following day based on whatever had or had not happened in the intervening hours. This system worked, within limits. It produced forecasts that were better than chance, that captured the broad statistical behaviour of solar activity with reasonable accuracy, and that gave infrastructure operators and space weather response teams a basis for planning. But the limits were real and significant, and they were not primarily limits of analyst skill or institutional commitment. They were limits imposed by the fundamental nature of the problem being solved. Solar magnetic systems are complex in the technical sense of that word, not merely complicated but genuinely non-linear, governed by dynamics that operate simultaneously across spatial scales, ranging from individual magnetic flux tubes a few kilometers wide to global coronal structures spanning millions of kilometers. The processes that determine whether a given magnetic configuration will erupt in the next 6 hours or remain stable for another 3 days involve interactions across all of those scales at once. Human pattern recognition, even highly trained expert human pattern recognition, operating on decades of accumulated observational experience, can only capture a fraction of that multi-scale complexity at any given moment. The rest lives in the data, in patterns too subtle or too high-dimensional for unaided human perception to reliably extract. This is precisely the category of problem that machine learning was designed to address, and over the last several years the application of these techniques to solar forecasting has begun to produce results that the field has been working toward for decades. Research groups at institutions including NASA, NOAA, and universities across the United States, Europe, and Asia have trained neural networks on the accumulated archive of solar observational data now available. Magnetogram sequences from the Solar Dynamics Observatory stretching back to 2010, historical flare catalogues compiled from decades of X-ray monitoring by the GOS satellite series, CME detection, and characterization records from SOHO's LASCO coronagraph, solar wind measurements from the Advanced Composition Explorer satellite positioned at the gravitationally stable L1 point between Earth and Sun. The training datasets now available are rich enough, and the computational resources available to process them are powerful enough, that the models being developed are beginning to find signal in the data that traditional forecasting methods could not reliably access. The results in flare prediction have been the most clearly demonstrated. Machine learning models trained on magnetogram time series have shown the ability to identify precursor magnetic configurations associated with major flare events at prediction windows of 24 to 48 hours, with accuracy rates in the M-class and X-class event categories that meet or exceed traditional expert forecasting benchmarks in controlled comparisons. The advantage is most pronounced for the larger events, precisely the category that matters most for space weather response, because the training dataset for major flares, while smaller in absolute event count than the dataset for minor events, contains the richest observational signatures. The models are learning something about what a solar active region looks like before it produces a major eruption that human analysts reviewing the same data were not consistently capturing. What exactly they are learning, which specific features in the magnetic field configuration are driving the predictions, is itself an active area of research, as interpretability analysis of these models reveals subtle field geometry signatures that were not part of traditional forecasting frameworks. The more recent and arguably more consequential development is the extension of machine learning techniques to the problem of CME arrival time prediction. Flare prediction tells you whether an eruption is likely. CME arrival time prediction tells you, after an eruption has occurred, when the resulting plasma cloud will reach Earth. These are different problems with different data requirements, but both are critical for the practical space weather response chain. A grid operator who knows a CME is coming but does not know whether it will arrive in 8 hours or 36 hours, faces a very different decision environment than one who has a reliable estimate within a window of a few hours. The difference between implementing protective measures now and waiting to see how the event develops can be a matter of hours, and those hours, in a fast-moving space weather event, can determine whether the response is adequate or too late. Current CME arrival time prediction carries uncertainty windows of roughly plus or minus 7 to 8 hours in the best cases, degrading significantly for complex events involving multiple successive CMEs or unusual solar wind conditions. Machine learning approaches trained on historical CME catalogues, incorporating initial CME speed and angular extent measurements alongside solar wind background conditions derived from real-time monitoring, are beginning to demonstrate narrowed uncertainty windows approaching plus or minus 3 to 4 hours in validation testing. A reduction of 4 hours in arrival time uncertainty sounds modest, stated as a raw number. In the context of space weather response planning, it is the difference between a grid operator having a reliable enough prediction window to take major protective actions, reducing load, disconnecting vulnerable transformer assets, adjusting grid topology to limit induced current pathways, and not having that window. The operational significance of that improvement is difficult to overstate for the specific scenario we have been discussing throughout this documentary. Beyond the prediction models themselves, the broader infrastructure for real-time space weather analysis has evolved substantially. The Space Weather Database of Notifications, Knowledge and Information, known as DONKI, maintained by NASA's Community Coordinated Modeling Center, provides a continuously updated catalogue of solar events, CME detections, and propagation model outputs that feeds into both operational forecasting and research analysis simultaneously. When a significant solar event occurs, DONKI aggregates observations from multiple spacecraft, runs ensemble propagation models, and generates probability estimates for geomagnetic storm conditions at Earth on timescales of minutes to hours after the initial detection. The system is designed specifically to function as a real-time analysis pipeline during fast-moving events, exactly the operational scenario that April 4th, 2026 could produce if the corona passage generates unusual solar activity. The specific relevance of all of this to the MAPS perihelion is worth making explicit. Whatever happens on April 4th will not happen in an observational vacuum. Every major solar monitoring spacecraft in operation, SOHO, the Solar Dynamics Observatory, Parker Solar Probe, Solar Orbiter, the stereo assets, the GOES X-ray monitors, will be collecting data in real time throughout the perihelion window. That data will flow into analysis pipelines that include both traditional expert review and AI-assisted pattern recognition running simultaneously. If the corona passage produces any anomalous activity, unusual flare signatures, unexpected CME launches, atypical plasma dynamics in the coronal region through which MAPS travels, the space weather monitoring community will identify it faster than any previous generation of tools could have managed. The latency between event occurrence and informed human awareness of that event has been compressed through a combination of improved instrumentation, faster data pipelines, and AI-assisted analysis to a degree that would have seemed optimistic even 10 years ago. This is genuinely reassuring, and it deserves to be stated clearly and without qualification, because the overall tone of a worst-case scenario discussion can sometimes obscure the real and substantial progress that has been made on the response side of the equation. The detection and prediction capability available in 2026 is not comparable to anything that existed during the Carrington event of 1859. It is not comparable to anything that existed during the major geomagnetic storms of 1989 or 2003. The tools have improved dramatically, the monitoring network has expanded substantially, and the integration of machine learning into operational forecasting represents a genuine step change in what is possible rather than an incremental refinement of existing methods. The harder question, the one that the reassuring progress on detection and prediction cannot fully answer, is whether the response capability on the infrastructure protection side has kept pace with the improvements on the observation and forecasting side. Knowing that a Carrington-class CME is arriving in 14 hours rather than in an uncertain window of 8 to 22 hours is a meaningful improvement. Whether 14 hours is enough time to implement protective measures for a power grid that was not designed with rapid reconfiguration for geomagnetic storm protection as a primary engineering requirement is a separate question, answered not by better AI models or faster data pipelines, but by infrastructure investment decisions, regulatory frameworks, and operational planning processes that have been moving on their own, slower timescales. We will see what is coming on April 4th. The instruments are ready, the pipelines are running, the models are trained. The question of whether seeing it coming early enough translates into being able to do enough about it in the available time, that question lives not in the space weather forecasting community, which has done its work, but in the gap between prediction and preparedness that modern civilization has not yet fully closed. Part 14. The next generation of solar observatories. To understand why April 4th, 2026 will be observed better than any previous sungrazer event in history, you need to understand the hardware that will be watching it. The story of that hardware begins with a recognition that took the better part of the 20th century to fully consolidate in the scientific community. The recognition that the sun is not a stable, predictable background condition for life on Earth, but an active, variable, occasionally violent star whose behaviour propagates outward through the solar system and interacts with every planet, moon and small body within it. Acting on that recognition required building instruments capable of watching the sun continuously, from multiple vantage points, across multiple wavelengths, through the full range of its activity cycle. The fleet of spacecraft now in operation around the sun represents the accumulated engineering and scientific investment of that recognition, built over decades and distributed across multiple space agencies and international partnerships. On April 4th, every significant component of that fleet will be pointed at the same event. The result will be the most comprehensively observed sungrazer perihelion in history, and possibly one of the most comprehensively observed single solar events of any kind. The centerpiece of the in-situ observation capability is the Parker Solar Probe, and its existence still carries a quality of audacity that familiarity has not entirely erased. When NASA began serious planning for a mission to fly a spacecraft through the solar corona, the engineering challenges were substantial enough that the mission concept had been discussed, deferred, and redesigned across multiple decades before the technology finally existed to execute it. The fundamental problem is thermal. Getting close to the sun means surviving an environment where the energy flux from the solar disk increases as the inverse square of distance, meaning that at Parker's closest approaches, the solar radiation intensity is roughly 500 times what a spacecraft at Earth's distance experiences. The solution was a carbon composite heat shield approximately 11 centimeters thick, capable of sustaining temperatures approaching 1400 degrees Celsius on its sun-facing surface, while the instruments sheltered behind it operate at near-room temperature. Building that shield, and building the systems to keep it precisely oriented between the spacecraft and the sun throughout the mission, was the engineering achievement that made Parker possible. Parker Solar Probe launched in August of 2018, and has since completed multiple perihelion passes on a trajectory that uses repeated Venus gravity assists to gradually shrink its orbit and bring it progressively closer to the sun. By 2026, Parker's closest approaches have brought it to within approximately 7.2 million kilometers of the solar surface, a distance that places it well inside the orbit of Mercury and well within the sun's extended corona. To put that distance in perspective, Earth orbits at 150 million kilometers from the sun. Parker is getting closer than 5% of that distance. It is not observing the corona from a safe remove. It is flying through it. The instruments Parker carries were designed specifically for the in-situ sampling environment of the corona and inner solar wind. The field's instrument suite measures electric and magnetic fields, radio waves, and plasma waves with high time resolution, capturing the electromagnetic structure of the coronal environment at scales that remote sensing from Earth distance cannot resolve. The sweep instrument assembly measures the velocity, density, and temperature of electrons, protons, and helium ions in the solar wind. The actual particle population of the corona, sampled directly rather than inferred from remote observations. The ICE-Sun ICE instrument measures energetic particles accelerated by solar events, providing direct detection of the high-energy particle populations associated with flares and CMEs. Together, these instruments do something that no previous solar observatory could do. They tell us what the corona actually is, measured from inside it, rather than what it appears to be when observed from 93 million miles away. What Parker has already returned from its early mission passes has forced significant revisions to pre-mission models of coronal structure. The solar wind, in older models, was expected to accelerate gradually and relatively smoothly away from the sun, reaching its characteristic speed of 300 to 800 kilometers per second somewhere in the mid-corona, before settling into the relatively steady flow that spacecraft at Earth's distance have been measuring for decades. What Parker found instead is a corona with dramatically more local structure than those models predicted. The solar wind emerges not in a smooth gradient but in a complex variable pattern shaped by the underlying magnetic topology of the corona. Regions of fast wind and slow wind alternate in a way that reflects the configuration of coronal magnetic structures at their source. The boundary layers between these different wind streams are sites of intense magnetic reconnection, the process by which magnetic field lines of opposite polarity meet, break, and reconnect in new configurations, releasing energy in the process. Parker detected these reconnection events directly, measuring the particle acceleration signatures and magnetic field disturbances they produce from within the boundary layers themselves. One of the most striking discoveries from Parker's early passes was the detection of what the mission team called velocity spikes, brief intense reversals and surges in the solar wind velocity profile that occur on timescales of seconds to minutes and appear to be associated with small-scale magnetic reconnection events near the coronal base. These features, termed switchbacks in the literature, were known in principle from remote observations, but their frequency, amplitude, and association with coronal source regions was not appreciated before Parker flew through them directly. The corona maps we'll enter on April 4th is not the smooth, idealized plasma environment of pre-Parker models. It is a turbulent, structured, locally variable environment where magnetic reconnection events occur continuously at multiple scales, where the boundary between coronal and solar wind plasma is more complex than previously understood, and where the interaction between an infalling cometary body and the surrounding magnetic field geometry will play out against a background of ongoing small-scale dynamics that older models would not have captured. Solar Orbiter provides the complementary perspective that Parker's design cannot, where Parker's extreme close approach trajectory prioritizes in situ sampling over remote imaging. The spacecraft is moving too fast and too close to the Sun to carry traditional imaging telescopes pointed at the solar disk. Solar Orbiter is designed to observe the Sun as an object, watching its surface and atmosphere from a moderate distance with a suite of remote sensing instruments whose resolution and wavelength coverage exceeds anything previously achieved from a dedicated solar observatory spacecraft. Launched in February of 2020 as a joint mission of the European Space Agency and NASA, Solar Orbiter carries imaging cameras in extreme ultraviolet wavelengths that reveal the thermal structure of the corona, spectrometers that can measure the velocity and composition of coronal plasma, and a coronagraph that blocks the solar disk to reveal the structure of the outer corona in white light. It also carries an in-situ instrument package similar in concept to Parker's, allowing direct sampling of the solar wind environment at its operating distance. The particular capability of Solar Orbiter that distinguishes it from every previous solar observatory is its orbital inclination. By using a series of Venus gravity assists to progressively tilt its orbit out of the ecliptic plane, the flat plane in which Earth and the other planets orbit, Solar Orbiter is gradually gaining access to viewing angles that have never been available to any previous spacecraft. The solar poles, which play a crucial role in the Sun's magnetic cycle and in the global structure of the solar wind, have never been directly observed by any instrument. Solar Orbiter is in the process of changing that, with each successive orbit bringing a higher latitude vantage point and progressively better views of polar magnetic structures that ground-based and ecliptic plane spacecraft can only observe at extreme foreshortening. The polar magnetic field configuration is directly relevant to the global topology of the corona through which maps will travel, and Solar Orbiter's observations of that configuration in the weeks leading up to April 4th will provide context for interpreting whatever the perihelion passage produces. Together, Parker and Solar Orbiter do something that no single spacecraft mission could accomplish alone. They provide simultaneous in-situ and remote sensing coverage of the same solar environment from complementary vantage points, with instrument suites designed to address the specific scientific questions that the corona passage of a large Kreutz sungrazer raises. Add to this the Solar Dynamics Observatory in Earth orbit, providing continuous full-disk imaging of the solar surface and low corona at multiple wavelengths and high cadence. SOHO, with its long baseline coronagraph record, enabling comparison to every previous large sungrazer event in the instrument era, and whatever stereo assets remain operational, providing off-axis viewing angles that allow three-dimensional reconstruction of CME trajectories, and the observational network covering April 4th begins to look less like a collection of individual missions, and more like a coordinated detection system assembled, almost by fortunate timing, precisely for this event. Every instrument in that network, on April 4th, 2026, will be writing data. Whether the data records a spectacular but ultimately benign disintegration, a survival that produces the comet of the century, or something that the models did not predict, The scientific record of that day will be the most complete record of a large sungrazer perihelion ever compiled. The generation of solar observatories now watching the sun was built over decades, motivated by the understanding that the sun's behaviour is not academic but consequential. April 4th is the day that investment meets its most demanding and most unprecedented test. The hardware is ready. The question is what the sun will give it to measure. Part 15, April 4th, 2026. The experiment the sun will run. Every story that science tells eventually arrives at the moment where theory meets reality. That moment has a particular quality that anyone who has spent time in research recognizes, a specific mixture of anticipation and humility that descends when the months or years of modelling, debating, and projecting are finally over and the universe is about to deliver its actual answer. You have done everything you can with the data you have. You have built the best models available. You have argued the probabilities with colleagues who disagree with you about the details and agree with you about the stakes, and then you wait for the experiment to run. The experiment does not care about your models. It does not negotiate with your uncertainty ranges. It simply happens, and then you spend the following years trying to understand what it meant. April 4th, 2026 is that moment for everyone who has been paying attention to Comet C/2026 A1. We have spent this entire journey building the case piece by piece, the unprecedented discovery distance that revealed an object far larger than any modern-era Kreutz sungrazer had any right to be, the anomalous brightness curve that has been climbing, with a smoothness that comet observers find either reassuring or deeply suspicious depending on which interpretation they bring to the data. The plasma physics of critical ionization velocity and coronal mass loading that transforms a comet's dissolution inside the corona from a simple evaporation event into a potential magnetic perturbation of genuinely uncertain consequence. The historical precedents, Lovejoy's survival, the Kreutz family's ancient lineage, the suggestive but unconfirmed correlations between sungrazer passages and subsequent CME activity. The geometry that places Earth at its closest approach to the comet's orbital path 2 days after perihelion, in the precise window when any triggered CME would be most likely to arrive. The Carrington event and what it would mean if something approaching its intensity were delivered to a civilization now comprehensively dependent on electrical infrastructure for its basic functioning. And the solar cycle that was supposed to be quiet and is not, providing an already energized coronal environment into which MAPS will deliver its cometary material. We have established through all of that two things that need to be held simultaneously. The probability of a catastrophic outcome is low, and low and impossible are not the same word. The distance between those two concepts is where this entire story lives. It is where every honest assessment of this event has to operate. And it is where we have to operate now, at the end, when the remaining task is not to build more suspense but to be precise. The most likely outcome on April 4th is destruction. MAPS enters the corona on its calculated trajectory. The nucleus encounters thermal and tidal forces that exceed its structural integrity, and it fragments. The fragmentation may be gradual, a progressive shedding of material over the final hours of approach, or it may be sudden, a catastrophic breakup at some critical point in the corona passage where accumulated stresses finally overcome cohesion. Either way, the end result is the same. The nucleus dissolves into an expanding cloud of gas, dust, and rapidly ionizing particles. The corona absorbs this material. Solar physicists watching the data streams from Parker, SOHO, the Solar Dynamics Observatory, and Solar Orbiter see an unusually rich and complex signature in the coronal plasma measurements, more material than any previous sungrazer has delivered, more ionization signatures, more magnetic field perturbations along the trajectory path. They publish papers. They refine their models of how large comets interact with coronal plasma. The science advances significantly, and on April 5th you wake up, check your phone, see that the comet is gone, feel a small, complicated mixture of relief and mild disappointment, and go about your day. The sky looks the same. The grid is running. The worst case did not happen. This is the most probable outcome. It should be stated first, stated clearly, and not buried under qualifications. The sun has absorbed countless sungrazers. The corona is extraordinarily good at consuming and falling material without producing anomalous consequences. The base rate of dramatic outcomes from sungrazer events is, based on every observation we have, very low. MAPS is larger than previous observed sungrazers. but larger does not automatically mean consequential in the specific way that the worst-case scenarios require. Destruction is the most likely story. It is a scientifically extraordinary story, the most detailed observational record of a large comet disintegrating inside the solar corona ever compiled. But it is a safe story. The second possibility is survival, and it is worth dwelling on because it tends to get overshadowed by the dramatic scenarios and does not receive the attention it deserves. If MAPS carries a nucleus that is sufficiently large, sufficiently dense, and sufficiently structurally coherent to survive perihelion passage, or even to survive in the form of a large surviving fragment, what emerges from behind the Sun on April 5th or 6th would be something the modern world has never seen. The brightness projections for a surviving post-perihelion MAPS are extraordinary. A nucleus retaining even a fraction of its estimated 2.4 kilometer diameter, receding from perihelion and outgassing at maximum rate into the inner solar system, could produce a comet visible in broad daylight, a tail potentially spanning tens of degrees of sky, visible to the naked eye for days or weeks as the object recedes, the comet of the modern era, a spectacle that would be photographed from every smartphone on the planet's daylit side and would introduce an entire generation to the experience of watching a comet with their own eyes in a way that none of the previous generation's significant comets quite managed to deliver. Survival would be safe, spectacular, and scientifically invaluable, providing direct data on the composition, structural properties, and behavior of a large Kreutz fragment that survived the corona, data that would reshape comet science in ways that destruction, however informative, cannot match. The third possibility is the one we have been building toward throughout this documentary, and it requires being described carefully because it exists on a spectrum rather than as a single defined outcome. An unexpected solar reaction, not necessarily a Carrington event, not necessarily a civilization-altering geomagnetic storm that darkens cities and fails transformers across 3 continents, but something that current models did not predict and cannot fully account for after the fact. An anomalously large CME launched in the hours following the corona passage, larger or faster or more energetic than the background solar maximum activity, would statistically produce on its own an unusual disturbance in the coronal magnetic topology traceable in its spatial and temporal characteristics to the trajectory of the comet's dissolution. A space weather event that, when analysed in the days and weeks after April 4th, produces a scientific consensus that what happened was not routine, that the cometary interaction contributed meaningfully to a solar eruption that the Sun's own dynamics, in the absence of that interaction, would not have produced at that time or at that intensity. This outcome would not end civilization. It would not necessarily even produce a significant geomagnetic storm at Earth, depending on the direction of the CME and the geometry of its propagation through interplanetary space. But it would change something fundamental about how solar physics and space weather forecasting think about large sungrazers. Every future Kreutz fragment of significant size detected on approach to the Sun would immediately become a space weather concern as well as an astronomical spectacle. The monitoring protocols, the response planning, the infrastructure protection frameworks that currently organise themselves entirely around the Sun's own activity would need to incorporate an external trigger category. That is not a small change, that is a reclassification of the threat landscape, and it would begin on April 5th, when the data from April 4th is analysed and the conclusion is reached that the comet did something to the Sun that the Sun did not do entirely on its own. And then there is the fourth possibility, the one that sits outside the probability distributions, the one that no model currently captures because building a model requires having observed something at least once, and this specific thing has not been observed, the plasma cascade that reaches a threshold whose location we have never been able to identify because we have never had an object massive enough to approach it. The coronal structure that destabilizes not in isolation, but in a way that couples through the magnetic topology to adjacent structures, triggering a chain release of stored energy across multiple systems simultaneously. The event that the instruments capture in extraordinary detail, and that the models, examined afterward, cannot fully reconstruct from first principles, not because the physics is wrong, but because the initial conditions were outside the range the models were trained on. Black swans carry that name because they were considered impossible until the moment of first observation. Their impossibility was not a logical conclusion. It was an extrapolation from incomplete data. The Sun has been processing comets for 4.6 billion years. The specific combination of a nucleus this large, a solar maximum this active, and an observation network this capable has never previously coincided. What that combination produces is, in the most honest possible framing, unknown. What April 4th ultimately represents, stripped of the probability assessments and the scenario rankings and the worst-case framings that have organised this entire discussion, is something more fundamental than any single outcome. It is a demonstration of the basic condition of existence on this planet. We live inside a dynamic star system. The Sun is not a lamp. It is a magnetically active, energetically variable star that interacts with every object in its environment, from microscopic dust grains to multi-kilometre comets, and those interactions produce effects that propagate outward through the solar system and sometimes reach us. For most of human history, we experience those effects without understanding their origin. For the last few decades, we have been building the instruments, the models, and the monitoring infrastructure to understand them in real time. April 4th is the day that entire investment faces its most demanding and most unprecedented test. Whatever the Sun decides to do with the object falling toward it at 550 kilometers per second, the data collected on that day will change what we know about comets, about the corona, about the relationship between the solar environment and the civilization that depends on it, about how often the universe runs experiments on us without consulting us first. The Sun has been here for 4.6 billion years. It has processed an uncountable number of comets in that time, in every configuration imaginable, under conditions that range from the violent early solar system to the relatively calm Middle Age it currently occupies. It has done all of this without an audience capable of understanding what it was watching. That changes on April 4th, 2026. For the first time, something large is falling into the Sun, and we're ready to watch what happens. Not with naked eyes or medieval terror or Victorian telescopes, with instruments that can measure magnetic fields from inside the corona, resolve plasma dynamics at scales of kilometers, and transmit that data to analysis pipelines running in real time across a global network of scientists who have spent their careers preparing for exactly this kind of moment. The Sun has seen comets before. It has never been watched doing it by us. Until now.